Right, come on in. Looks like we're still got some chairs here. Hey, all right, well, it's 8 o'clock. I'll get us started on our second day here and kind of recap of what we did last time, which, as I was trying to say, was Chapter 1 and kind of a review. I trust the homework went well for you. Make sure you turn it in on the way out of class, or if you're kind of still scribbling on it, as some of you emailed, that's fine. Let's get it turned in, though, in the lab today. So that's also my way of reminding you is, yes, we do have our first lab here for today. And not a surprise, it's going to be a lab on motion, which is exactly what we're going to get into. So hopefully you've got a chance maybe even to look ahead into Chapter 2. But like I said, that's where I want to get us started here. A kind of a quick recap of what we did on our first day, and now really get what I would call into the course material. Actually start some physics today, and actually see some physics that you most likely have seen or have, well, I guess what I want to say is, first thing, we've done some new physics. What I mean by all that is, on Wednesday, is we went through this chart, and probably everything we did you had seen at one time or another. And I kept saying, remember what you did in kindergarten, remember what you did in third grade, remember what you did in middle school. And so we put them together. Now, it was probably a different approach than what you saw in middle school and in high school. And so now that you are smarter and more intelligent, we tried to put together the meaning behind the symbolism of the metric system. And I hope I got this point across here, that we had a bunch of quantities and we reasoned out the next quantity. And that's what the physical world is. And you'll see that today. We start off and we ask the next question. Well, what about this? And so you remember those 4 steps. We thought about a new quantity. After that, we came up with the equation for that new quantity. After that, we came up with the units that would be used to measure the new quantity. And then finally, the 4th thing, we studied those units. We gave ourselves a physical understanding, a physical interpretation of what those units meant to us. And you're going to see that same thing here today. At least I hope so. In fact, you're going to see it hopefully every time we get together. We're going to ask the next question. And so that's where I want to begin then today. Now that we went through things like area that you had seen before, and of course I kept asking you, what if you had never seen it? So, when we left on Wednesday, we were talking about things like distance and time and a bunch of other quantities. But let me put that back on the door. You remember, I'm back on the board. You remember us talking about this distance from door 1 to door 2. And we said, all right, the distance between those 2 doors is roughly 10 meters. And so we wrote out the equation, of course, and then we went into a detail of why do we write it as a 10m. Let me not repeat all that. But let's also say that the time it took to get from that door to that door. And if I remember right, we said I could walk kind of slowly over there and it would take me about 5 seconds to get over here. So again, imagine, if you will, me standing here and saying, okay, I'm going to walk over to that door. And I'm going to take 5 seconds to walk over to that door. And so we could talk about how much time would it take, how much distance would it take. But now I think you're ready for the next question. And this one you have seen before. You saw it in your Physics 102 class. You might ask yourself, at what rate are you traveling? How much distance do you travel every second? I mean, I know it's going to take a whole 5 seconds to get all the way at the 10 meters. But what about partway in between? What about after 2 seconds? How far have you gone? In other words, how far are you going each second? And so, not a surprise, we could then come up with a new quantity. This new quantity is asking about a rate. How much distance do you travel each second? And I know you're familiar with this quantity, so I won't bother to ask. I'll just put it on the board. Velocity. You did it in the Physics 102. The symbol we like to use for velocity is the lowercase v. I even alluded to it last Wednesday when I said I'm not going to use the small for volume. I'm saving that for velocity. And so here's our velocity. But let's go through those 4 steps again, like you had never seen the word velocity before. The first idea is you have come up with this concept. You've given it a name, velocity, and a symbol v. But what do you really mean by that? What are you trying to say here? Well, I'm trying to define a quantity. I'm trying to understand a physical part of a rate of motion. How much distance do I travel every second? So that means you would write down, okay, I would travel some distance and divide it by how much time did it take to go that distance. And so that's what you were saying in verbal form, or at least I was saying in verbal form. But that would be what I'd call step 2. So step 1 is you've thought about a new quantity. Step 2 is you thought about it, you put it into an equation. I don't know, maybe we should take one more step before we put it and call it a complete equation. Whoops. But there would be your equation. Distance divided by time. In the case of these numbers that I'm talking about, it would be simply 10 meters, 5 seconds. And now, I can do the mathematics. I know you know that 10 divided by 5 is 2, fair enough. And as we talked about on the first day then, we have the same mathematics with our units as we do with the numbers. And so there's nothing here that would cancel. There's nothing we can put together and square like we did a bunch of things on Wednesday. We just have to leave that alone and call it meters per second. And so that would be the answer. The answer would be, okay, your velocity must be 2 meters per second. And so that answers this next question. What would be the units to measure this thing called velocity? So let's see, I guess I've done 3 of the 4, right? I thought about a new quantity to get the day started. As I thought about it in terms of words, I converted that into an equation. Okay, so there's my equation. From there, I actually did a calculation and found out what are the units to measure this new quantity, which we're going to call velocity. And probably the most important thing, I don't know, it's debatable, they're all important, but that last one, step 4, is what does it mean? If I were to say your velocity is 2 meters per second, what does that mean to you? Well, I guess it means I'm traveling 2 meters every second. And it's really that straightforward. It is, if I were to stand here at the door in 1 second, I guess I would have gone 2 meters. And in the next second, 2 more meters. And in the next second, 2 more meters. Uh-oh, I'm not going to quite make it, huh? 2 more meters. And after 5 seconds, I made it to the end. And there's my 10 meters. And so it's 2 meters every second. Now this one too, you've already seen. So we probably don't need to dwell much time on this, just like all the other ones we did on Wednesday's lecture. But this hopefully resets that tone of think about what the next question is. Write out the equation. Get the units for that. And interpret those units. What do we mean by meter per second, 2 meters per second, 3 meters per second? And that's this whole idea. But let's take it one step further. One step further that you did not do in your Physics 102, although you probably did a little bit already in your calculus class. What if it was a little different motion here? What if I were to take 5 seconds to go there, but let's say I start kind of quick and then I get tired, and so then I slow down and I finally get to the door. Would anything up here change? Yeah, nothing I've done up here would begin to change, but there is something I want you to see. And of course, one thing, the whole reason you took your calculus between Physics 102 and coming here is so we can talk about situations like this. And so here is our new step, if you will. If I were to put a plot here and say, all right, I'm going to plot my distance versus my time. And if I kind of describe what I was doing, it might be something like this. I might have started off and increased at a very fast rate, and then maybe at a different rate. But the point is, I did go 10 meters after 5 seconds. I just wasn't always going 10 meters every second. And so maybe to be a little more precise here, I should rephrase this. I should really call this an average velocity. Let's use the symbol from our math class, and maybe I'll ask you guys, are you familiar with the bar overrun? Yeah? All right. And so velocity, you put a bar over it, you mean average velocity. And so a little more accurate here is to say that what I have just been talking about for the last 5 minutes here is really not velocity per se as in instantaneous velocity that we will mention here. This is more of an average velocity. This is saying take that whole distance and divide it by the whole time. So on average, I went 2 meters every second. But in what I just described for you, starting off really fast, I probably did those first 2 meters in less than 1 second. But over here, where I got tired and now was going slow, then it would take me more than 1 second. So on average, I did 2 meters every second. Well, this just begs the next question. What should we do next? I mean, if what we really did over here was then talk about then an average velocity, which now I will put a bar under here, now I'm beginning to say, you know, this really has more to it. And so the next question is, what is my rate of travel at that instant? Let me call that a v without a bar on it. What is my instantaneous speed? Okay. Well, like I said, this one is somewhat new to you. It's new in a physics class. It's probably not new to you in the sense that you probably approached this in your calculus class. It's a standard problem that calculus teachers like to do, should do, in order for students to comprehend why are they doing their calculus. But let's say you've never heard of instantaneous velocity before. And now for the first time you're beginning to ask that question. Well, I want to know, what rate am I traveling at that instant? How would you define it? Well, isn't it a distance traveled in time? Well, that's what we had for average velocity. So what's different here?
Time.
Okay, what about the time?
It's a small time.
Oh, okay, so you are saying maybe this is a short amount of time. Right? That's kind of the difference. Okay, fair enough. And so that's how I would describe instantaneous velocity. It is still a rate like average velocity, but what's important, as you pointed out, is that it's a small moment in time. So it's the limit as time goes to zero. All the more reason we learned our calculus. What is this? Does this look familiar to anybody? Isn't that the definition of a derivative? So doesn't this say the derivative of position with respect to time is the instantaneous velocity? Now let me put a box around that, because that is the one that is new for you. This is the one that fits that prescription that I was saying on Wednesday. Here it is, the goal of the class. Take the concepts of your Physics 102 together with the math you have learned, and particularly recently your calculus, and let's merge them together. And this is kind of our first step of doing that together. We have taken the concept of velocity that I know you saw in Physics 102, together with the concept of a derivative, which I know you saw in your Math 150, and let's put it together. And what we are trying to say is, if nobody had ever told us that the instantaneous velocity is the derivative of position, didn't I just figure it out? By reasoning through, of saying, what am I looking for? What is the math involved? And so I have come up with the concept and now the formula. That's my point. And so we're going to spend the whole semester doing that. We're going to hopefully ask ourselves a lot more questions and answer the why questions instead of how. Well, how do I solve this problem? Okay, well, why is it written out this way? Why is the velocity important? What's the issues involved? And so we're going to be asking a lot of whys. And things that you haven't seen before is the whole trick. You come up with yourself. A lot of deductive reasoning. I said it on Wednesday. It's worth saying many, many times. You're only going to learn 6 things before this semester is over. Newton's 3 laws and the 3 conservational principles. All of which you've seen before in Physics 102. Conservation of energy, conservation of momentum, conservation of angular momentum. Newton's 3 laws. The first one, the law of inertia. The second one, F equals ma. The third one, action and reaction. Those 6 things we're going to put together. That and a lot of deductive reasoning, and that's going to be the hard part. The reasoning out the problems. And so that's what I'm trying to lay the foundation for. I have just come up with the formula. Had I never seen it before? And it's possibly that some of you in this class had not seen that instantaneous velocity is the derivative, although I suspect most of you have, because you did this in the calculus class, right? Yeah, and so most of you are shaking your head. Yeah, exactly. Let's keep going with this. What about the units? What about the units to measure instantaneous velocity? Are they the same as average velocity? And again, for many of you, this is probably the first time you've actually thought about what are the units associated with this little calculus operation called the derivative. Are there any units here? Are there any units in this one? Well, probably the thing to remember that you probably didn't do too much in your calculus class is coming back to here. Remember what this is. This is the limit as time goes to 0 as this ratio. Doesn't this ratio have units of meters there? And doesn't this ratio have units of seconds there? The little symbolism just means a small distance and a small time, but it's still a distance, so it must be measured in meters, and it's still a time, so it must be measured in seconds. So again, not a surprise, even though perhaps I've never really dealt with the units associated with a derivative, I can now see that there would be units, because every time I see a derivative, I can go back and think of it as a limit of 2 small things, the quotient of 2 small things. That can actually be very helpful. A derivative really is a quotient, right? Because keep in mind, like the problem we did on Wednesday, if I pull into the gas station and I look up at the sign and it says gas costs $2.50 a gallon, and I pump 6 gallons, remember this problem? How much does it cost? And we came up with $15. You multiplied them together. And you remember me asking me, why did you multiply them together? Well, it made logical sense. Of course you would multiply them, because really what you're doing is you're putting 1 gallon in, okay, that's $2.50. You're putting another gallon in, that's $2.50. You're putting in a 3rd gallon, that's another $2.50. You're putting in a 4th gallon, that's another $2.50. And so you're just adding $2.50 6 times. Repetitive addition is multiplication. You learned that back in 3rd grade. And you just applied your mathematics. Exactly right. You knew when you were supposed to multiply. You knew if you were repetitively adding something together, you would multiply. Fair enough? And so I'm asking you, do you know when you're supposed to take a derivative? Because there'll be a number of problems that you will see. And I can't tell you how many times that students get stuck on them and they go, I don't know what to do. And they ask me, well, how do I do this? And I go, oh, well, okay. Well, if we take the derivative, and they're like, oh, I'm good from here. I got it. Really? The problem was me just saying, take the derivative. Yes, that's an important step and a hard step. When do you take a derivative? Why am I taking a derivative? Well, if it helps, remember this. This is what a derivative is. A derivative is a ratio. And that's what's really kind of new. This is an applied mathematical course. All of you have gone through calculus. And you're probably pretty good with your calculus. But as you will see, your calculus that you do here will have a kind of a different flavor to it. Because you will never come across a problem that says, take the derivative of this function, which is probably all you did in your calculus class. This one sets it up, and you've got to take the derivative. So none of the derivatives we take are really hard. They're not like those real hard ones, like take the derivative of the inverse tangent of the natural log of this binomial. There's none of those where you got to do the chain rule, and the chain rule of the chain rule, and the chain rule within the chain rule. That's not usually our challenge. Our challenge for this class is, oh, I was supposed to take a derivative. Why did they just say that? No, that is the problem. For you to realize I'm supposed to take a derivative. So a slightly different bent on it, and hopefully you can see it now. So I'll say it again. Had nobody ever told you that you're supposed to take the derivative of position to get velocity, you could have reasoned it out. You would have started out by, what do you mean by velocity? From that, what do you mean by instantaneous? From that, put it together with a little bit of math, and you got your equation for velocity. Fair enough? All right, well, last part, which we probably don't need to spend much time here either, but now that we've seen the calculus with units, we see that we have meters per second for the units that measure instantaneous velocity, just like they did for average velocity. Again, not a surprise. And so when I ask to interpret it, when I say, what does 2 meters per second mean to you? Well, that means that's your rate. Now, since it's an instantaneous velocity, it doesn't mean that I'm always going 2 meters per second. But what it does mean, at that instant, if I would continue at that rate for a whole 1 second, I would go 2 meters. But since my speed may increase or decrease, I may go more or less than 2 meters. So to say my instantaneous speed is 2 meters per second does not imply I will go 2 meters in 1 second. It does imply something about the rate, though, and you could answer it as, if I were to continue that rate for a whole second, I would go 2 meters. Okay? And so that one, I think the interpretation of the units, you probably have a good handle on. But I like to start the day and this chapter with this whole idea of an extension from things you have done to things that maybe you haven't done, or at least why do you do it the way you do it? Okay? And these are going to be those questions. In fact, it's probably worth coming back to this graph at this point and saying, let's look at this graph. If I were to talk about its average velocity, what would it look like in this picture? Well, I guess I would do a rise of 10 and a run of 5. And so when you talk about the average velocity, you could also, on a graph, say, well, it is the slope of the line connecting those 2 points, right? So you can kind of visually see on a graph what is average velocity. All right? Visually on a graph, what is instantaneous velocity? Right. And you guys did this in your calculus. It's worth repeating here again. What is this really saying? Well, this is saying take the change in position after a small amount of time. Why don't I do it here at the beginning, right here? And say, all right, if I wanted to know my instantaneous speed here at the beginning, I would take a short distance, maybe 1 step, and divide it by that time. And even then you might say that is too long of a time. Then I could take a shorter amount of time. But let me just do that first step. Let's say the first step took me all the way to here. And I think you could see, trying to bring back those memory cells of your calculus class, which you probably are now because you guys are just got done with 150 most likely, and you're probably in 160 right now. And running through all this again, but you can see then that if I went distance divided by time, that would be the slope of those 2 points. But to make it more visual, I would say the instantaneous velocity is the limit as time goes to 0. And so maybe I should take a point that is even closer in time, or closer in time, and closer in time, and closer in time. And so like you did in your Math 150s, you took the limit as those 2 points in time got closer and closer, and essentially they became 1 point. And so you were looking then at the slope that only touched the line, or the curve I should say, at 1 point. You know what we call the tangent? And so you learned, and hopefully you learned why, not just you learned, that the derivative gives you the tangent when you look on it on a graph. And that's the reason why it gives you a tangent. I would even go far to say, had you never learned in your calculus class that the derivative gives you the tangent, couldn't you have just reasoned it out right now? Right? By the meaning and the definition behind what do we mean by the limit as time goes to 0? We mean that these 2 time frames are getting closer and closer and closer together. So on a graph, as we look at them, we look at the slope of a line where the 2 points get closer and closer and closer, and in the limit they become 1 point. We're looking at a line that only touches a curve at 1 point. That is a tangent. And so what else could it be? Of course, nobody needs to tell me that the derivative is the tangent. I can think it through on my own and come up with it. Okay? But again, you've seen that before. And so a lot of the things we've done so far, you've seen before. And that's why it's worth going through that logic to point out you could come up with it on yourself. You could reason it through. Because that's what you're going to see more and more of as the semester goes along. Things you haven't seen before. Things that the only answer is you've got to work it out. You've got to think through the puzzle. And so you've got to rely on the things that you do know, which in our case, our goal is to take the things you do know from Physics 102 together with the math you do know from 150 and below and merge them together and start working on some more complicated motion problems and mechanics problems that you did not see in 102. And that's why this is a step up. Fair enough? All right, well, I'll keep going, because that's really the first section here of chapter 2 here, is to kind of introduce you to what is instantaneous velocity. Why is it the derivative? Why is it measured in meters per second? What does it really mean? All right, well, let's continue this discussion a little bit further. I mean, the whole reason we brought up discussion of instantaneous velocity versus average velocity is because we said that when you make a long distance from here to that door, you may not go the same speed the whole time, right? As I was saying, I may start off really fast and then get tired about halfway and then kind of slow down and finish it. So as we said, over here, your instantaneous velocity would probably be more than 2 meters per second. Over here, it would be less than 2 meters per second. Seems like I should ask the next question. I wonder how much I changed by in terms of my speed. I mean, I was going real fast, and then I'm going real slow. Did I decrease my speed by a lot or a little? I don't know, but it would be nice to have some kind of way of measuring, right? How much did my speed change? Ah, there we go. There's my next question. There's my next quantity, right? Maybe I should be looking at, what would we call that? Yeah, and I heard some of you muttering it already. You learned it in your 102 class. What was acceleration? Yeah, it's that next question then. It is, okay, so now we've given the option of the velocity changing. At what rate does it change by? And so there becomes our next new question, which becomes our next new quantity. And so let's talk about it, because as we talk about it, we should have an idea of what does acceleration mean, which means we should be able to write it in terms of an equation, something we can calculate it, so we can figure out what the units are and an understanding of those units. And so I'll put over here, okay, here's this new idea, acceleration. How do I define it? Well, I guess I'm really saying it's the rate of change of the velocity, right? How quickly did that change? Did I start at a high speed here and go to a low speed, maybe at the same rates until I got to my low speed? Or was it more complicated than that? Was it here that I started out with a large speed and I actually kept this large speed, and then I just gave up right there. And I went right to the slow speed, and then I just continued with the slow speed. See, those are two very different scenarios. Yes, you certainly did the 10 meters in 2 seconds, but how did you change your rate of speed? Did you do it over the whole 10 seconds? Did you do it right in the middle where you dropped down from 5 seconds to, in 6 seconds, and so it only took you 1 second to change the speed? Or maybe even less than 1 second to change your speed? Or maybe over a longer time, like 3 seconds, but not as much as the 10. I don't know, but that is a good question, a good quantity to come up with. So, there's my new thought process, my new quantity. Acceleration. Let's talk about it for a while. And of course, just like we did with velocity, we should do the same thing we did in 102, but we should also now incorporate our Calculus 150 and take it one step beyond we did in 102. So mathematically, how would I write this? How would you put that in an equation? What are you saying here? Okay. Glad you said derivative, but I'm going to hold off on that, right? I mean, my first step is to say, this would be the definition of acceleration. How does its speed change in a given amount of time? And so coming back to this graph that I have since erased, but looked something like this, where I went to 10 meters in 5 seconds. And now that we said, all right, this red tangent line would be its speed when time is equals to 0. And then this red tangent line would be the speed when time equals to 5. That's what that graph would be saying, right? And kind of this description we've been going through might have this at a higher rate of speed. Maybe it's 4 meters per second, so I start off really fast. But near the end, I'm going really slow. As we said, the average is 2 meters per second. Okay? But maybe this would give me a description of those 10 meters. Well, looking at those numbers, I would say, all right, I've got a 4 meters per second, and I've slowed down to a half of meter per second. Oh, hang on. Maybe I better be careful with my sign here at the beginning. Let's do this. And so I'll put in here my final speed of a half a meter. My initial speed, 4 meters per second. The time that it takes me to slow down is this 5 seconds. So it looks like I have a negative 3.5 meters per second and a 5 seconds. Is that a 0.7? 0.7 meters per second each second. Oh, negative. And so I would say that is my acceleration. But again, there's quite a bit of interesting discussions here that we should have. First of all, I'll start off with the same discussion we had for velocity. Does that mean I change my speed the same amount all the way through? No. What have I really then solved for here? Yeah, and I think then I really need to put that this description is really an average speed, right? I mean, as we look at the units and an understanding of it, so maybe we can finish this part of the chart here, we could say, all right, now that I think we've got the idea and we've got the formula, what are the units then to measure acceleration? What's this? Good. Some of you hesitated a little bit. But this is the most complicated units we've done so far. Not that this is real complicated. They're going to get a lot more complicated than this. But this is what we would call in math a compound fraction, right? And so this brings us back to Wednesday's lecture, right? Use the same mathematics with your numbers and your units. So how do we simplify a compound fraction? Don't we flip and multiply? And so this becomes meter per second squared. And so I know you've seen the units for acceleration, but had you never seen the units, as we were talking about on Wednesday, this would have led to the final step of, yes, these are the units, meters per second squared. And so just like we came up with the unit for meters squared and meters cubed, we've come up with the units today for meters per second, and now for our second quantity, meters per second squared. And so I think we've done 3 of those 4 steps, right? A new idea, the formula that goes with that idea, the units to measure the new idea, and then an interpretation. And again, I think this is the hardest one we've done so far. What does point, and maybe we should finish it over here. So average acceleration of negative 0.7 meters per second squared. What does that mean to you? What does the 0.7, and even we should talk about the negative 0.7, meters per second squared mean? What does meters per second squared mean to you? Yeah.
Your velocity is changing every second.
Right, and I think it's probably better to come back to this step. Remember, this is equivalent to that. But this says meters per second each second. And so the acceleration is saying, how does your speed change? What you're really telling me is you're changing by 0.7 meters per second every second. Now, of course, it's a negative, so what do you mean by that? Well, let's come back up to the math. Let's make sure as we do the math, we're always reading the math. Don't just do the math. Read it. Look carefully at it. Remember I said a few moments ago, and I'll keep saying it throughout the semester, this is an applied math class. And a lot of these problems will really foul you up if all you do is try to do the problem. You got to read the problem. What does each step mean? What does a negative mean in here? What does a meters per second each second mean to you? And the 0.7 is probably the easiest part of all. But as I come back up here and I read the math and I begin to see it says final minus initial. What this means is I am going to get a negative number if what? Well, if initial is bigger than final, then I will get a negative number. So if I didn't catch it before, I can look at this and say, well, the negative is telling me it's slowing down, right? And the 0.7 means that it is slowing down by numerical value of 0.7. 0.7 meters per second each second. And so coming back to this step here, as I start here, and as I described earlier, I'm starting off pretty fast. I'm going at 4 meters per second. But according to this, 1 second later, how fast am I going? Yeah, I should decrease by 0.7 every second. So if I'm starting here at 4 meters per second, a second later, I have now gone down to 3.3 meters per second, at least on average. More on that in just a second. But after a second later, on average, how fast am I going? Another drop of 0.7, right? So was that 2.6? And so this means change your speed by 0.7 meters per second each second. And of course, that's on average. So let's keep going, because as you can see, this is algebra. And it brings up this question. Am I really changing by 0.7 meters per second each second? If I come back and look at this graph, I would say probably not. This line's pretty steep. A second later, it's probably right here. Oops, not a very good line. But I would say the slope of that one and the slope of that one are not much different. And so looking at that graph during that first 1 second, it doesn't look to me like it changed by much. Although, it starts to look like when it gets into this area, there's some big changes that go on. And so the slope changes a lot. Remember, the slope is the speed of it. And so I guess a little more accurately would be to say at the beginning part there's really not much change, and then there seems to be this area right from about maybe here to here where there's a large change in my speed. And then to continue on, there is still a change, but not by much. So again, hopefully not a surprise here, but you are asking this next question. Not as what is the average, but it might be nice to know what is the acceleration. Let's see, how shall I write this? I guess I'll write this. The change in speed per time, but during a very, very short moment. And so like we did for velocity, this is we're saying what is the instantaneous acceleration. And so that we will use the symbol A for. And so just like we saw a few moments ago for velocity, there's an average velocity and an instantaneous velocity. The average velocity and the instantaneous velocity are conceptually the same in the sense that they measure a rate of change. But of course, the instantaneous is saying, what is it doing in that little moment in time? The limit as time goes to 0. And now we can do our calculus again. What would you call this? The limit as time goes to 0, as the rate of velocity changes with time, would be the... And are we back to our derivative? Right? Derivative of what? Velocity. With respect to what? time. And so there would be my formula for the instantaneous rate of change, the instantaneous acceleration. And that's what I meant, and I'll say it again, by taking the physics that you learned in 102, because I know you learned all about acceleration in 102, but you did a lot of algebra. You did a lot of average accelerations. What you didn't do in your Physics 102 was the calculus with it. And that's our next step up. So again, taking the calculus that you learned in your Math 150, together with the physics that you learned in 102, let's merge them together and say this is what we have. So again, we have that concept of acceleration. We have the formula for acceleration. We have the units for acceleration. And maybe it's worth pausing again to say, now that we're taking a derivative instead of just a quotient like we did in our Physics 102, what would the units be? Would the units even change? No. And like the last one, you guys are shaking your heads. No, because again, anytime you see a derivative, even though you probably haven't with derivatives yet, that's what you're about to do now. You see that a derivative really is a algebraic quotient. And so if those were the units when we did our algebra, they of course would come out to be the same. This would be meters per second for velocity. This would be seconds for time. You would end up with meters per second. You would then have a compound fraction that you would flip and multiply and then write as meters per second squared. Maybe even say it as meters per second each second to emphasize what do we mean by an acceleration of 0.7 meters per second squared. We mean it would change by 0.7 meters per second each second. Okay? And so there is our second. And I might point out our last little quantity for the chapter. That's what this whole chapter is about. This whole chapter is about velocities and accelerations. How are those connected to position and time? Those four quantities: position, time, velocity, acceleration. If those made sense to you, you've got all the tools you need to do all the homework. With that said, I would encourage you to get started on the homework right away, because you may find that you're going to have a lot of questions throughout the week. And particularly by Friday, I don't want you to be working on it Sunday night and go, oh, now I got a lot of questions and it's due tomorrow. Okay? But that is our whole strategy here. But let me kind of clear off the board here. In fact, let me clear this off. I think we can erase this, at least until we get to some new quantities, which we will in Chapter 3. Well, really not even till Chapter 4. But for this chapter, we've just covered everything. And when you get a chance, and hopefully you will soon, tonight to read this, read it through and you'll see that's what the author spends. He spends the whole chapter explaining, and it's not that long because there's not that much to explain. What makes the chapter hard, if it is hard at all for you, is not so much that it is all these whole ideas and all this stuff to read. It is, how do I use this? How do I take these ideas and how do I apply them? How do I figure out where this rocket is supposed to be? They gave me a description of the rocket and then they asked me, where is the rocket after 18 seconds? That's where it gets hard. Can you actually use it? So if I were to summarize what we have done so far, I would say we have talked about position, velocity, and acceleration. And those are connected. Because velocity is what? Well, it's the rate of change of position. Velocity is saying, at what rate am I changing my position? And so what I'm trying to get across to you is, if you know position, couldn't you get velocity? Let's try the other way around. What if you know velocity? Could you get position? What would you do? Right, what is the opposite of a derivative? Right, that integral, or sometimes referred to as the antiderivative. Purposely, right, it undoes the derivative. So again, this class is going to ask you to put together your Math 150, your calculus, together with your Physics 102 and merge them together here. And so if I happen to know velocity, I can then get to position, right? That's what this is saying. Know one, I know the other, right? In fact, let me continue on with this chart, because the second thing we talked about here is acceleration. And our definition of acceleration was the rate at which our velocity was changing. And so after a couple of steps of thinking it through, we realized that if you took the derivative of velocity, you would get acceleration. And again, I know you've done that before in your calculus class. But my point was, had you never done that in your calculus class, you could have come up with that on your own, right? You could have said, well, it's a derivative. That's what we mean by a derivative. And I'm going to ask you the next question here. What if it was the other way around? What if I had given you the acceleration and asked for the velocity? Could you get that? What would you do? Yeah, the inverse operation, right? You would integrate acceleration. When you integrate acceleration, you would then get velocity. And so that was your calculus class. Probably felt like a long, hard class at times, but you only did two things. You did a derivative and its opposite. That's it. Right? Again and again and again. And that was the main idea. What is the usefulness of that operation and its inverse operation? Yeah.
Don't you need either the velocity or always for the position of one to exactly know what was happening? So when we integrate, we get a constant.
Okay, fair enough. When we integrate, we get it with a constant. And so depending on how much information the problem gives us, we may or may not know that constant. I think is what you're saying, right? Right. Yeah, so yeah, I agree. In fact, I'm about to do some examples for you here, but right, the first part here, I'm just trying to give you this abstract idea, right? You would integrate it, but you're right, and I'm going to ask that in just a second. You would integrate, and of course, what you learned in your math class is when you integrate, you get a constant. And that constant, of course, means something, and so that's where I'll start saying, well, read the math. You may be able to figure out what that constant is. They may have given you enough information. They usually do. Not all the time, but sometimes they do. All right, so before I kind of finish up this chapter and say, all right, here is the connection. I'm going to put over here on the side, I'm going to put a big box around it, highlight the box again and again and again, and emphasize. What is the point of this chapter? This is the chapter in a nutshell. It is the connection between position, velocity, acceleration, and time. Those four quantities are interwoven, and you can go from one to another. How much, like you said, depends on how much information they give you, but we should be able to go back and forth between. If they give me velocity, I could then take its derivative to get acceleration, or I can integrate it to get its position. Right? Or if I know its acceleration, I could integrate it once to get its velocity. I could integrate that then again to get its position. And so if they give me this rocket ship and they want to know its position 18 seconds later, and all they've given me is the acceleration, couldn't I integrate it twice and get the formula for position? That's my point. And that's what you'll see us do here in just a second. And so, as you guys are getting ready to do your second chapter and do the homework this weekend, let me help you. Do you want to know all the answers to all the homework problems here before you go for the weekend?
Sure.
There it is right there. Okay? That's exactly what you need, and that is all you need to do all the homework problems at the end of the chapter. Now, that's not to say they're easy, because they are not. And you will see some hard ones. But I can guarantee you this, that this is the answer to them. Of course, then they start getting real hard because not only do the accelerations keep changing, they throw a second object out there. And then the two objects start at a different time. So you got to keep track of, okay, what's the time when the first one started to move and what's the time after the second one started to move. And of course you have two different objects, so you have to keep track of position of object number one and position of object number two. And so the details is what throws students off and make it hard for them. But let me assure you, if you keep thinking about this, you will be able to do just fine on all the homework problems. So let's do this. Let's start off with what I would call the easiest type of problem I could give you. What if we give an object that has acceleration, but it never changes? A constant acceleration. Now, that's not to say every problem has constant acceleration. Fair enough? In fact, most problems don't have constant acceleration. But for us, at the beginning, most of ours will have constant acceleration. It seems like the best place to get started. It's the easiest one here. So let's have a discussion here about problems that have a constant acceleration. In fact, to emphasize it here, I'm going to say let A equal a constant. All right? So I'm going to limit this next discussion to special case. A special case that only has constant acceleration. But as I said, there's a lot of problems we could have with a constant acceleration. For example, you could be in your car and the light turns green and you step on the accelerator, and as the car goes forward, you would say, all right, the car has an acceleration of, let's say, 2 meters per second each second. And it doesn't change. And of course, we can talk about that conceptually. I want to put it mathematically. But if it always has an acceleration of 2 meters per second each second, that means a second later it would be going a speed of 2 meters per second. And a second after that, it would have a speed of 4 meters per second. A second after that, it would have a speed of 6. A second after that, 8, right? And that's what's meant by an acceleration. And that's what's meant by a constant acceleration. Always change by 2 meters per second each second. There are many constant accelerations. I know in Physics 102 you learned something called a free fall. There's an example of a constant acceleration. Do you remember free fall? What was free fall?
Acceleration to gravity.
Okay. The word free was in there. Why? Because what if you only have gravity and it's free from everything else, including air resistance? If, in other words, if I came over here and I dropped these two objects, do they have a constant acceleration? And do they have the same acceleration? Do you remember that from 102? Now, I'll drop them again here, but they do hit at the same time. We would call this, I guess, a free fall, although it's not technically a free fall, because what else is going on? Yeah, they are hitting the air. But if they're going slow enough, I can kind of ignore that. So I'm going to call them a free fall. Would this be a free fall? Would all three of these fall at the same rate?
No.
How come this one was so much slower?
There's more.
Air resistance. So is it free fall? No, right? So again, this word free fall is nice, but it implies there is nothing helping and nothing hindering the object from falling. And so free fall has a special acceleration. Do you guys remember that acceleration? Good. We use it so often that we like to use the symbol G. What is it? 9.8 meters per second each second. Meaning a falling object would change its speed by 9.8 meters every second. Now I know there's actually air resistance, but if I went to a tall building and I dropped it, after 1 second, how fast would it be going? 9.8 meters per second. After 2 seconds, how fast would it be going? 19.6, right? It would increase by 9.8 every second. And of course, by that time, it's going pretty fast, so I'm not sure I'd call it free fall anymore because it is interacting with the air. It might be nice to review this one and just show it if you haven't seen it. I don't know from your distance if you can tell, there's a feather right here and there's a penny. And so when I turn it, you can see that they don't seem to fall at the same rate. The penny's already at the bottom and the feather is taking its sweet time. And so is this free fall? No. Maybe I'd say it for the penny. The penny doesn't seem to be having much problem with the air, but the feather does, right? So free fall, no. What if I took the air out? And so if I hook up my vacuum tube here, and give it a chance to remove all the air, then I should have free fall. Then these two objects should fall without any interaction to the air. And they each should fall at the 9.8. And so now, I think you can see they fall together. And they fall at that same rate. So again, one of the things you saw way back in 102 is that all objects under free fall have an acceleration of 9.8. So keep that in mind. Eventually we will get to harder problems where we have to include the effect of the air. That's chapter 6, by the way. A tough set of problems too, by the way, but let me not scare you quite yet. We'll wait till we get there to chapter 6. But for right now, we will just use a lot of free fall. And so one example of a constant acceleration is free fall. All right. So again, keep that in mind when you come to the problem. So again, let's keep our discussion here. Let me take and say, what if A is a constant? Whether it be the 2 meters per second each second that I mentioned for my car, or whether it be dropping an object and its acceleration is 9.8 meters per second each second, or maybe it's some other problem. If it's a constant, let's talk about that. Could you give me an equation for the speed? If I told you the acceleration is a constant, could you then tell me the equation for the speed? Well, how would I go from acceleration to speed? There it is right there, right? There's the answer to all the homework problems we're going to do. Right? I'm giving you this. I'm asking for that. How do you get there? Right? The antiderivative. You're going to integrate it. So let's give it a try. Let's use some of our calculus with our physics. That is the new piece this semester. And so we're going to take our 102 and add together with our calculus here. All right, so according to that, velocity, the equation for velocity would be taking the acceleration and integrating. And maybe now you can see why I took this special case. If A is a constant, what would you do here? Take it out, exactly. So I'm going to take the A, and because it is a constant, I can pull it in front of the integral, right? You remember learning that from your Math 150, right? That's the nice thing about linear operators, and an antiderivative or an integral is one of those linear operators. You could pull the A out in front. So I'm going to pull it out in front. Good. Now, notice I can only do that if a is a constant, right? So would this be valid for every problem involving physics? No. Again, just this very important beginning special cases. Okay, and so again, let's talk about the easy one here. We're only in chapter 2, right? So constant acceleration. So if it's constant acceleration, I'm going to pull it out in front. Now I can have the integral here. Could you do that integral? What is the integral of dt? Yeah, it's just t. And so as I said earlier, we're not going to do real hard integrals here. But we are going to need to know why you would do the integral. And so I think on this problem involving calculus, it's not the integral itself that is hard. It was this step when I asked you, how am I going to go from acceleration to velocity? You've got to know, oh, I got to do an integral. And of course, as you pointed out earlier, I'm not done. What else goes here? Yeah, when you do a integral, and I'm going to call it C1 for now, some constant, there has to be a constant of integration. And let me not repeat your Math 150 class, but I'm sure that you went through this in your calculus class of why is the constant needed. I want to go one step further. What does it mean? I mean, now I know it's needed, and I'm going to put it in my equation. Does it mean anything to me? And this is the part I'll keep alluding to. Read the math. Don't just do the math here. Okay, I mean, I did the math. I did the integral and I put a constant, right? But don't stop here. Does this have any meaning to you? I mean, what have we done so far? Well, we got velocity equals, and we got this equation, yeah?
Would C1 be like the velocity that you start at?
Exactly. I would say here, think about this whole equation, and particularly, what about when time equals to 0? If time equals to 0, what would you get here? So what velocity would you get when time is equal to 0?
C.
Yeah, you would get that constant, that C1. So what this really is saying is this constant of integration is really saying, what is the speed when time is 0? So to help me remember that that's what C means, let me not write it as a C. I'm going to give it a little better notation. How about if we write this as V sub I? The V for velocity, the sub I for initial. This is what I would call the initial velocity. And if I do that, then this equation, and I'm going to change the order and put initial velocity first so that it looks like the same formula you'll see in your textbook as you read your textbook. And please read your textbook. There's no way that you can learn everything, I say, and you hear it one time and you'll learn it. Learning, unfortunately, doesn't work that way. People need to be told multiple times before it sinks in. So you'll see I'll tell it to you here in lecture. I'll tell it to you again in lab. I hope you will also then read it in the book and then also do it when you do the homework problems. And after those 4 exposures, hopefully now all these ideas will set in. And if they don't, that's of course why we got the video. So you can go to the YouTube and scan through and say, what did he mean on that part? I'm going to go back and look at those 5 minutes. Yeah.
Physics 102 teacher really disliked our book. What do you think about this book?
Oh, I like this book. Yeah. No, I think you'll get a lot out of this book. I would even go so far as to say that I'm not saying anything that the book isn't saying. Now, that's not to say you should only listen to me and not read the book, and it's also not to say you should only read the book and not listen to me. It is to say do both and you get a chance to sink in because it's a lot of material. But and I'll try to follow his pattern, and that's what I mean by I'll use his notation. So he uses a sub I. He writes it in this order. He calls this equation number 1. He calls it the kinematics equation for constant acceleration, number 1. Makes sense, right? Because it's an equation, and remember, it's limited to what? constant acceleration. I've said that many times to make it sink in, because not every problem you will do has constant acceleration. We do a lot of them at the beginning because they're the easy ones, but we're going to hopefully wean you off the easy ones and get to the harder ones. And when we get to the harder ones, please don't come back and use this equation. Go back and do what? Do the integral. And if you know something about the acceleration, then integrate the equation for acceleration. Exactly. And it probably be a harder integral than just pull it out in front and then get a t and add a constant. Well, let's try this again. Could you give me the equation for position? Again, under the same circumstance where we have constant acceleration. Yeah?
Well, you take the integral of the equation you got for velocity.
Exactly, right? I'm going to come back over here to emphasize, here's the answer to everything we're going to do in this chapter. I've just done this. I started here with acceleration, I've integrated it once to get velocity. So you're going to do the same thing to get position. You integrate the equation for velocity. And we just got it. And so this equation, of course, which is only valid for constant acceleration, but that's what I'm asking for. Could you give me an equation for position if you had a constant acceleration problem? And sure, I'd come over here and say, okay, here is position. Position is then the integration of velocity. And I should say the integration with respect to time. And so let's put that in here. We've just solved this one. And so here's the integral. And I'll put initial velocity plus acceleration times time dt. You might say it's a little harder integral, but I don't think unreasonably hard. It's certainly stuff you've been doing in your 105. Again, we're back to that linear operator. It should have these two pieces here. Maybe I'll even write it as two steps to kind of get us started. But that's one nice thing we learned about the antiderivative, or integral. They're linear operators, so I can do the two pieces separately. All right, so let's go ahead and do this. What's the integral of this one? Okay. And again, let's make sure we're reading it. VI. What is that again?
Initial velocity.
Initial velocity. When it comes to my math, my calculus here, can I do anything with that? Can I pull it out in front? Is velocity a constant? Good, you caught that. I was getting a little confused here. Is velocity a constant? No, doesn't this say velocity changes with time? But this is initial velocity. This is just a number, right? This is the speed that it has at time equals to 0. Maybe it was 7, maybe it was 0, who knows, but it's some number. And the best part about that is you can pull it out in front. And let me not write it in two steps. Then what integral of dt is t. Plus a constant? All right, let me hold off on the constant for just a second. But remember, I haven't forgot about it. All right, let's do the second one here. What would I do here? Well, I guess like I did in that first term and like I did back here, a is a constant, at least for this special occasion. All right, so a is pulled out in front. So I'll put the a by itself. But then what do I have? I have an integral of t dt. What's that? Yeah. T squared over 2. Plus a constant, right? I haven't forgot about it. I just haven't put it down quite yet. All right, so there's my two integrals. Now again, notice, probably not hard integrals. Again, because I think the point that makes the math hard here is not so much the integrals we do, but knowing that I was supposed to take the integral. Now, let's look at those constants. There was one here and one here. Can I add them together? And what do I get?
Initial position.
Okay, I get some constant that I still don't know about it until I begin to read the math here. But I want to point out, I'm not going to write two separate constants. There's no point in that. I know that I'd get a constant from one integral. I know I'd get a constant from another one. I know I could combine those to get some other constant, so there's no point in writing 2. There would be 1 up there. And then now let's do what you said. Couldn't we read this math a little bit? Like we did back here? Let's not leave it as a constant. I mean, that's what we learned in our math class, but let's go beyond that. Let's not just do the math, let's read the math. And as we read the math, as we study it, what does C2 mean here? Well, like before, at time equals to 0, that would be 0. And that would be 0. So at time equals to 0, x would be C2. So knowing that, why don't I give some kind of symbolism to that C2? Instead of just saying, hey, it's some constant, but let's give it a physical meaning. And I think you're seeing that it would be the position when time equals to 0. Let's call it x sub I, the I for initial. This would be that initial position. And so let me write this then as x equals, and so I will have initial position plus initial velocity times time plus 1/2 acceleration time squared. And so that, putting it in the same order as your author, is equation number 2, if you will. And I'll just refer to it as equation number 2. Technically, it's a little more than that. It's equation 2 for kinematics. It's also only valid for constant acceleration. So it's the kinematics constant acceleration equation 2. All right. But again, it could be a very useful one if you know things like what is the initial position and initial velocity acceleration, and they ask what is its position after 5 seconds. We can put in the time, we can calculate its position. Or the other way around. We know its position and the question says how much time would it take to get there? And so we can solve for time given its position. In that case it's quadratic, but again we've done algebra and so we can solve a quadratic formula, and we will here, but that would be an approach of using that particular problem. In fact, as long as we're here, let's do some more mathematics here, because there are some problems that often say something like this. Let's take a race car, for example. You take a race car at the starting line. So it starts from rest. You could even call the starting line the initial position. So we know its initial position and we know its initial velocity. Okay? And we say something like, okay, the race car then, now maybe make it a little bit harder here. What if we said something along these lines? We want to know what is the position when the race car is traveling, say, 60 miles an hour. Well, let's think about that. We start off with this race car, and as I said, it's on the starting line, so we know its initial position and its initial velocity. And I don't know if I made it clear. I was starting to say, and we know the acceleration here, and then I just told you the speed, right? 60 miles an hour. Couldn't we use this equation to solve for time? And then put that time into here to get the position? Let's do that symbolically. And that's what your author does. He ends up calling this equation number 3. I guess I want you to see it is nothing more than the combination of 1 and 2, although 2 is nothing more than the integral of 1, and 1 is nothing more than the integral of a. But let's give that a try here. Let's say something to this effect. Here's this race car, and we're told its acceleration. And the question is, what position is it when it's going 60 miles an hour? So this first step I would solve for time. I'd come over here and say, time is, and I would say velocity minus initial velocity over acceleration. Right? That's what I would get for equation 1. Now, if I was actually doing the problem and I gave you these numbers of the variables, and so this sounds like an excellent equation if you don't know time. And you're not looking for time, I should maybe point that out too. And that's the kind of thing I'm describing. I'm describing a situation where the problem is, what is the position of the race car when it is going 60 miles an hour? We don't know how much time it takes. That's the whole reason we have to do step 1 to get time and then put it into step 2. And so as you look at this, we would know everything about this race car. We know the initial position, we know the initial velocity, we know the final velocity, that is the velocity when we want to know what is its position. And so we could put everything into here. Fortunately, this simplifies quite a bit. You'll see it here when I put initial velocity times velocity over a, and the second term is initial velocity squared over a. That's the distributive property here. Here, here's the a minus b, the binomial squared. So let me write that, and I'll do the denominator first since that's easier, but there's the a squared. But this will be the a squared minus 2ab plus b squared. Right. And of course now if we put and cancel an a on top and bottom, we could then do the distributive with this 1/2. And you'll see then that we have some like terms. I'll go ahead and leave the first ones alone here. But you can see this first one is a 1/2 final speed squared over a. The second one, the 1/2 and the 2 cancel off, so it's v and initial v over a. And this last term has a 1/2 initial speed squared over a there. And this is what I was saying is after a little bit of algebra here, we can begin to see that there are some like terms. In that case, they cancel off. One's a plus and one's a minus. You can even see this a little bit. That initial speed squared and this initial speed squared, these are like terms, although this has a coefficient in front of 1/2. And that has a -1 in front. So they don't cancel off, but it does come out to be then a -1/2 initial speed squared over a when I put those two together. And then I can put the final speed squared over a. Let me do a little more steps of mathematics so it'll look like your author here. He puts the distances together. Kind of makes sense that this would be the distance the race car or whatever the object is traveled, so final minus initial. He puts this with a common denominator, changes the order a little bit. He moves the common denominator over to a x minus x naught. He even then moves the initial speed so that it becomes a positive and puts a little box around it and says this might be useful at times. It is connecting the final speed with the initial speed and distance traveled. And that would be a perfect equation for that description that I just gave you for the race car. Something that does not have time in it. And so here is, like I said, a great equation. It does not have time in it. This is probably a good time for me to pause. Am I going to spend all semester numbering these equations? 1, 2, 3, 4. If I do, by the time we get to the end of the semester, I'm going to be at something like 10,000. Well, maybe that's a little high. Are you really going to remember all 10,000 equations? No. too much. And that's not the point here. At some point, hopefully you'll get out of this. Do you want to know all the answers to all the homework problems? Don't try to memorize all 10,000 equations. This is the idea. Did you see that all 3 of those equations I got from here? Oh, are you going to memorize this first one? I'll let you make the judgment call. You can either integrate or memorize it. Since this is not a hard one, most people memorize this one. I get that. And I even agree with that. Am I going to memorize the second one? Well, it's nothing more than the integration of that, although it involved a couple of steps, and it's not too hard, and you'll use it so much that you'll probably just memorize it just because you used it so much. So I would probably say, yeah, memorize this one. Most people do. It's not too much to ask to memorize 2 equations. But as this goes on, do you see it becomes very obvious at some point, don't memorize the equation, work it out on the particular problem. And I think we've really got to that point when we got to equation number 3. Are you going to memorize number 3? Some people have really good memories, and for them, this makes more sense to remember it. For others, their analytical skills are a little bit stronger, and it makes no sense to memorize this one. Doesn't it just mean that what I could do is take equation number 1, solve it for time, get that, and plug it into here? So it becomes a judgment call on your part. Do you want to take and solve a problem with 2 equations or with 1? Obviously solving it with 1 sounds a lot easier, but then you got to memorize this equation for the test. So it's kind of your choice. I've done these problems so long that I can't help but memorize that one, and so I've memorized it, and it might be a good idea to memorize those 3. I don't know. It's kind of a judgment call. What I want to get to your point here is that there are going to be just a few simple ideas, and everything is worked out from there. It's worth pointing it out again. I did it once on Wednesday. I'll do it once today. I'll probably do it once every day between now and the end of the semester. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. If you find yourself realizing, hey, I could do these problems if I just had this massive cheat sheet on the test, you're missing the point. Which, by the way, no, you don't get a massive cheat sheet on the test. The point is you can do this entire chapter with that picture in your head. That's all you need. If you want to take an extra step and put that in your head and that in your head, I would encourage that. This one, kind of questionable. I have it, so maybe you'll want to too. I'll do this again for a 4th equation, a 5th equation, a 6th equation, a 7th. Stop at some point, okay? Don't memorize the next 1,000 equations that I'm going to give you. It makes no sense. That's not the point. We do a bunch of equations and put them on the board, not so that you'll remember them, but that you will generate them for the specific problem at hand. Okay? So be real careful with this idea that you think, oh, I got to memorize all these. I have all these formulas. No, that's not what physics is about. Physics is about thinking about the puzzle. The connection between position, velocity, and acceleration and time are really quite simple. They're right there. Okay? So let's do equation 4. Why not? Let's keep going. Let's keep going until we get to 1,000. No, we won't go that far. At some point we'll just say, let's just start doing example problems and work out whatever equation we need for that specific case. There's no point in doing 1,000 of them. I think by the time we do this 4th one, you'd get the idea that there's all kinds of combinations of problems that can be given to you. And so now the best thing is to look at some of them. And so that's what I'll do, is start looking at some of them. And hopefully that will give you enough skills that then you can sit down on the homework and go, well, he didn't do this problem in class. No, but it is connected to time and position and velocity and acceleration. So I can work it out. And there may be tens of thousands, maybe even hundreds of thousands of different problems that are out there. You don't need to see them ahead of a time. You can just walk into the test and go, I've never seen this problem, but I know it's connected between time and position and velocity and acceleration, and there's the answer. Okay? That's the big picture. All right, let's keep going because there are other problems that can be done. For example, the problem I was mentioning with the race car, I gave you the acceleration and said, what is the position when the race car is going 60 miles an hour? Let's change the problem. Let's say the problem still asks, what is the position? Okay. When the race car, what's the best way to do this, is going 60 miles an hour, so almost the same question. But this time, instead of giving you the acceleration of the race car, I give you the time. Yeah, that would be a good one. So the race car then has been racing for, say, 2 seconds or something, which at first step you would come over here and say, the race car's been going for 2 seconds, let me put that into here. But since I didn't give you the acceleration, you can't really get what the position of the race car is. But of course what you could do is you could come over here to equation number 1 and say, all right, you've given me the time, the initial velocity, and the final velocity. Couldn't that give me the acceleration? And once I use equation number 1 for acceleration, couldn't I substitute it into equation number 2? And then wouldn't that give me an equation for position that would be missing acceleration? So it's kind of like we just did here, except on this one, we knew acceleration and didn't know time. That's why we solved the first equation for time and plugged it into here. So let's do that again. Let's take equation number 1 and solve it for acceleration. And so again, knowing these other 3, I could get the acceleration of that race car. Now, once I know the acceleration of that race car, I could plug it into number 2. Now, if this was a problem out of the book, they probably would give me numbers and I can actually calculate it. I just have symbols here, so let me continue on in this symbolic notation, but I will write out equation number 2. And equation number 2, where I see acceleration, I will put this little formula that we got from equation number 1. So again, I'm taking that same strategy. I'm combining 1 with 2. And this game can continue. I can combine 1 with 3, right? I could, instead of solving 1 and putting it into 2, I could solve 2 and put it into 1. There's a lot of combinations I could do, and I think this last one is a good place to stop to show you that we can't do all the combinations. What you need to do is read each problem carefully, think through it, and know or figure out what to do between the studying what you know and what you don't know. I'll simplify this, but before I do, let me make the same comment. You see what I have now? I have an equation that is going to give me position, and it does not involve acceleration, right? So just like equation number 3 is a great one to use if you don't know time, what we will call equation number 4 will be a great one when we don't know acceleration. We've eliminated it from the problem. And algebraically, it's a little bit easier. This one got kind of messy there by the time we squared everything. But this one, as you'll see here in a second, has, let me cancel off a t there first. But there would be the first term, and there would be the second term when I do the distributive property. And we have 2 like terms right here. So that plus 1 minus 1/2 makes a plus 1/2. And that's kind of nice because we do have a 1/2 in each term and a time. So it's kind of nice to factor out a 1/2. Whoops. And factor out a time for these guys. It's also kind of nice to move initial position together with final position on the other side of the equation. And that's how your author does it, so I'll do the same here, so that hopefully between you watching me and then you reading the book, we, are saying the same things to you. But as you look at this, you'll see that it kind of makes sense to group these together, just like we did over here, because when you group them together, you're saying, how far did the race car travel? The final minus the initial. And of course, if you call initial position 0, it makes it even easier, just, that one just goes away. But so I'll group those together, and then you can kind of see that this would be the average speed, wouldn't it? This would be what your final, and this would be your end. You add them together, and if you divide by 2, that's your average. So you're talking about an average speed multiplied by time give you distance. Makes sense. I should warn you, though, especially with this one. Isn't this only valid for constant acceleration? See, everything I've been doing for the last half hour-ish has been with constant acceleration. We started it way back here. I said that everything you needed for this chapter is right here, but I said let's do a special case. And that special case is constant acceleration. So we got equation 1. And I think it's hard to remember that this one is only valid for constant acceleration because there's no a in it. But remember, where did it come from? It came from combining 1 and 2 together. With both 1 and 2, and particularly 1, because 2 came from 1, but 1 came from the integral. Okay? So I'll say it again. These are your 4 constant acceleration kinematic equations. You can memorize all 4 of them, or just the first 2, or even none of them, although it's probably, like I said, in your best bet to at least memorize the first 2, maybe even the first 3. This one we use periodically, but not too often. And we should stop there. But you can see, couldn't we combine these in different ways and get equation 5 and equation 6 and equation 7? And so I think this discussion has done enough to kind of point out that there's all kinds of combinations we could do. And the point is not to go through every combination and have you just memorize a sheet of equations and come in and plug them during the test. That's not the point. The point is, can you do a problem that you haven't seen before? Can you work it through? Do you know the bigger picture? Because if you know this bigger picture right here, the first thing you just have to ask yourself is this a constant acceleration problem? If it is, then you can know that you can use equation number 1 and 2 to solve them. If it's not, well, that means you're just going to come over here and actually do the calculus. You're going to do the integral or the derivative, depending on what you're trying to get accomplished. Well, what I want to do then for the rest of the week, which is only about 20 minutes for today, or 25 minutes today, and then all day on Wednesday, is let me show you by example. Let me open up the book. Let me just look at problems. Let me start doing problems. And as I do the problems, I want you to follow along. I will, if you will, kind of train that brain, get you to think, how am I going to solve these problems? And so, I have the book, at least the 7th edition here, in a PDF form. Let me turn to chapter 2 and say, all right, let's look. At chapter 2, problems. And see if I can remember. I think I want to say 140% is too big. I think 100% is a little too small. Oh, got nothing at the moment. Display on. Input. Oh, I think it needs to be on the computer here. Hang on. See if that does it. Ah, good. Okay. Okay. So here we are in chapter 2. And chapter 2. Let me look at my notes. Which one did I put here first? Let's look at 46. 46 is a good one. I'll maybe clear the board here a little bit. 46 kind of takes us back away from the algebra and the calculus for a second and more of a graphing picture. But I thought it would be a good place to get started with what I call concrete examples. All these I were doing is what I often refer to as abstract examples. And so that race car that I've been talking about are more abstract. I didn't actually put any numbers in here. But I think you'll get more out of it when I start actually putting some numbers in here. And then this, like I said, illustrates it well. And so 46 is right there. And it looks like I can make it a little bit bigger. How about if we do 110%? Can you read that in the back? No? A little bigger then? Okay. Should I go to 140%? Maybe that? Can you read that in the back? Yeah? Yeah? Okay. All right, so let's look here at number 46 here together. And it simply says this. A student drives a moped along a straight road. Now let me pause right there. I don't know if you caught this, but it's probably worth mentioning. We've been only working with things going in a straight line. I didn't really specify whether they were going horizontal or vertical or along an incline. So all those options are possible. But did you notice that we did not really do any kind of description about moving in the x-axis and the y-axis so far? All right, that's coming. Right, that's what we'll do after this chapter. But to start as simply as we can, let's only move in one dimension. So they say a straight road. That's important in this chapter because that's all we've really learned so far. At least in this class. I know you've already had Physics 102, so you've learned two-dimensional motion. But for this class, we've only done straight lines. All right, so moving on a straight road, as described by the velocity versus time graph below. All right. It says sketch this graph in the middle of your graph paper and then A, directly above your graph, sketch the position versus time, aligning the time coordinates of the two graphs, and then B, sketch a graph for the acceleration versus time directly below, again, aligning the time coordinates. I'll pause right there and say, okay, let me give that a try here. So let's see. I don't really have graph paper here, but I can put velocity versus time here. Right above it, I can put position versus time. And as they ask right below it, I can put acceleration versus time. All right, well, to get us started, let's do what they ask here. Let's copy that graph. It looks like the moped starts at time 0 and it goes for about 9 seconds. The first 3 seconds it increases, it looks kind of like a straight line until it gets to 8 meters per second. All right, so it looks like that is 8 in units of meters per second. And the time is in seconds. And so this is at about 3 seconds. And so I'm going to put a 3 seconds on each of the other two graphs. It seems to change here. Then you'll notice that it's pretty much flat, meaning it keeps the same velocity for 2 more seconds. So there's a 5, and there's a 5. And then it seems to slow down and come to a stop. And I didn't look closely enough. It was that's at 7 seconds. All right. So at 7 seconds, we're here. So it came to a stop. Only 2 seconds, whereas it took 3 seconds to get to that speed. And then, for whatever reason, the moped turns around and starts going fast in the negative direction. So it has a speed in the other direction here. And it looks like for 2 more seconds, 9 seconds. All right. So, all right, I think I've copied it well. All right. Got the picture in your mind? Remember all that description we just did between position, velocity, acceleration, and all that wonderful mathematics? Is this a constant acceleration type of problem?
Each segment has a constant acceleration.
How would I know if the acceleration was constant or not? Does this graph tell me anything about the acceleration?
Because the velocity changes.
Should I put this chart back on the board? Position, velocity, acceleration. Aren't they giving me velocity right there? How do I get to acceleration? Don't I take the derivative? Right? And what would the derivative look like on a graph? Isn't the slope? Right? All right, so doesn't this have a constant slope from here to here? But it's a different slope from here to here? All right, so this is my answer to, is this a constant acceleration problem? Well, I would say no overall, but I would say from 0 to 3, we do have a constant acceleration. From 3 to 5, we do have a constant acceleration. And from 5 to 9, not just 7, but 5 to 9, don't we have the same slope all the way down? And so the whole problem is not a constant acceleration, but it is a, what you might call in math, a piecemeal equation. They're pieced together with constant accelerations. And even though that question says plot this one first, I think I'm going to do this one. I've already done it. And so what would the acceleration be for 0 to 3 seconds? Well, what's the slope of this? Rise is 8, run is 3, right? 8/3 or 2 2/3, however you want to phrase it here. So I'm going to take a little mark here and say, okay, here is the 8/3. And from 0 to 3 seconds, I have a constant acceleration. Isn't that how you draw a constant acceleration, right? A level line, same value for the whole time? Sure. Okay. And so you can see what we're doing. We're just saying, do you really know how to interpret your mathematics? Take the physical picture, right? Use your mathematics. Apply your mathematics, right? Okay. How about from 3 to 5? What's the acceleration there? Yeah, 0, so I'll just do that. And I guess the acceleration probably curves real quick, and so you can see in that graph it kind of arches over a little bit. So you can see the slope is going from a slope of 3/8 and then quickly changes to a slope of 0. So quickly changes to a slope of 0. And then what happens here at 5 seconds? Yeah, it quickly changes from a slope of 0 to a slope of, so what's the slope of this one? And I would just do this part of it right there because it goes down 8 and over 2. So the slope of this is 8 over 2, that's 4. It should be the same as that. Now it's a negative 4, isn't it? All right, so quickly changes to a negative 4. And that's one of the 2 pieces. I think that was part B. Sketch the graph of acceleration. So I have a graph of acceleration. So it seems to have what I would say 3 constant accelerations. It's got the first part where it's going faster. Then it's got the next part where it has no acceleration. In other words, it just keeps the same speed. And then it's got another part, and interesting here is it's the same acceleration from here to here, it's slowing down. From here to here, it's speeding up, but it's speeding up in the negative direction. Okay? So maybe this is a good time to answer this question. If I came over here and I told you the acceleration is a -2 meters per second each second, is the object speeding up or slowing down? Yeah, we don't know if it's speeding up or slowing down. Well, let's read this carefully. Right? Acceleration is the change in velocity, right? You would get a negative number anytime, right, that, at least in terms of positive numbers, if the final is more than the initial, for positive numbers. But what about for negative numbers? Right, and so if this point right here is the origin, if I go in a positive direction, a positive acceleration means I'm going faster and faster and faster and faster. My final speed is getting bigger and bigger and bigger. But what if this is the origin and I'm going that way? And my speed is getting faster and faster. Doesn't that mean that I am getting more negative speed? Doesn't that mean my final speed is a bigger negative number than my initial negative number? So wouldn't that be a negative acceleration? Right? So be careful here with the sign here. Negative acceleration doesn't necessarily mean it goes slower. And you can see that right here. Doesn't this whole thing have a negative acceleration of 4? Isn't that what that's saying? But is the moped always slowing down? No. Right here, the moped is slowing down and comes to a stop, and then what? Turns around and starts to head in the negative direction. And it begins to go faster and faster in the negative direction. So that's what a negative acceleration means. And so be careful here. Like I said, this course will really press your brain on your understanding of your mathematics. You're going to read the math. Don't just do the math. Really understand what is the meaning behind the numbers. What is the meaning of subtraction? What is the meaning of multiplication? What is the meaning of a derivative? What is the meaning of an integral? It is an applied mathematics. You have had a lot of mathematical courses in your day. You have had very few, if any, applied mathematics. This is probably the only applied mathematical course with calculus you have ever taken. Because the applied mathematics you have used, maybe you did a little bit in chemistry. I know you did physics 102, but that was all algebra. It wasn't calculus. Okay? But apply the meaning of these. And so you're going to keep me hearing me saying that again and again. Read the math. Don't just do the math. It is so easy to think, oh, a negative acceleration means it's slowing down. No, let's read it carefully together. That is not what a negative acceleration means. And I don't need to tell you that. You can read it. And that is my overall theme I've been saying for these last couple of days. All right, let's try the other side here. The other one is to plot the position. Okay? And so I have that much information. Let me come back to this chart up here. How do I go from velocity to position? Well, there it is, the antiderivative, right? We integrate here. Okay. So I'm going to go ahead and call the initial position 0. They don't really say what the definition of initial position is, but I'm going to take this moped that's starting with a velocity of 0, wherever that is. I'm going to call that the initial position, so I can put it on the graph somewhere. 3 seconds later, what is the position of the moped? 12. Good. How'd you get that?
1/2, like it's like a triangle to the area.
Right. What I know is that to go from velocity to position, I do an integral. But I also know from my calculus that the integral can be visually represented by the area under the curve. So just like a derivative can be visually represented by the tangent, the integral can be visually represented by the area. That's sure one of the principles you learned in your Math 150 course. So knowing that, I can just look at the area, and since it's a triangle, how easy is that to get the area of a triangle? It's 1/2 base times height. So the height is 8, the base is 3, that's 24, half of that is 12. And so I'm going to put a little mark here at 12 and say, yes, that is the position of the moped. It is 12 meters away after 3 seconds. But I'm going to take this one step further. Aren't these two connected? How do I draw that? Do I draw it with a straight line? Do I draw it with a curve? And if it is a curve, what kind of curve? Is it a exponential? Is it a parabola? Is it a hyperbola? What is it, and how do I know that?
It's a line. It's a constant velocity. Wait.
Well, maybe I should write some more here on the board. Didn't we just do this set of equations a moment ago? Now, granted, we called these equation 1 and equation 2. And granted, they were only valid if we had constant acceleration. But don't we have constant acceleration from 0 to 3? So wouldn't these equations be valid? Wouldn't this equation say that when you have constant acceleration, shouldn't you get a straight line? Isn't that what this means? Taking you back to your Algebra 1 class, right? Y equals mx plus b. Right? This equation of a line. Not a surprise, I have a line. Sure. And of course, it's this other equation that I'm focusing on. This equation says I should have what? Parabola, right? Again, I think that's Algebra 1, or is that Algebra 2 where you do parabolas? Probably still Algebra 1 here. But again, read carefully and go back to your Algebra 1 and say, look, this is saying that position is related to time. Yeah, sure, and it's a parabola. So I should be able to make a parabola. Oh, concave up or concave down? Well, it depends on the sign of that. And during those 3 seconds, don't I have a positive? So that would be concave up. And so that's how I would draw it. Right? So you see all these answers? There is a logical reason I can go through to get the answer. I'm not just guessing or assuming anything here. Right? And I wasn't told to draw the parabola. I knew it was a parabola because I reasoned out that it was a parabola. I got the 12 because I knew it was an integral. And I knew the integral was the area of the curve. And they gave me the graph. Right? Yeah, I'll keep going. Where is the moped after 5 seconds? Well, kind of the same logic. The position would be the integral. The integral is represented by the area under the curve. This is 8 by 2, so this area must be 16 more. We already did 12 over here. So that's saying we're going to do another 16. All right, so another 16, that's another 12 and a little bit. So it's like 28 here. So after 5 seconds, I should be at 28. And I can ask that same question. How would I draw the line from the 3 seconds to the 5 seconds? Or would it be a line? Would it be a parabola? Exponential? Hyperbola? Okay, yeah, I would do the same thing. It definitely is a constant acceleration. So it's got to match these equations, but it's probably the easiest constant acceleration. Its value is 0. So I'm looking at this and you put a 0 there, what do you get? Isn't that a line? So, whoops, terrible line. But there would be the position. And now maybe we'll go a little bit faster here. What about the next 2 seconds? Yeah, it would be that area, which would be, what, 8. And so we've got 8 more. And I didn't give myself much room to get 8 more on there. But I'll just put a 36 at the very top there. But before I even draw it, let's keep going. Doesn't it have that same acceleration, not just for 7, but to 9 seconds? So what kind of path would I draw during that time frame? And again, not just 5 to 7, but all the way from 5 to 9. What shape is it going to be? Yeah, it's a parabola again, and it's concave down because we have an acceleration of negative. Concave down, right? It's a negative 4. In fact, you can even see that the area of this one and the area of this one are the same areas, just with a negative. So this would be an area of +8. This would be an area of -8. Which makes sense. It's losing position. And so at 9 seconds it should be here. And so it should come back to the 28, and it should peak at the 36. And so it should be a parabola concave down that is peaking at the 7 seconds at that 36 and goes down there. And so I think I've answered that one. And hopefully I've answered it in a way that would show you that you could have answered all of those, right? There's nothing here that I didn't do that you don't already know. All I've done is to say, let's get some information from our math. We did some algebra, we did some calculus, and we kind of put it all together with the information we have. And in fact, you can even see here that we've answered these other questions like, what is the acceleration at 6 seconds? What is the position? And all those good things. Maybe it'll be a good place to stop. I was thinking we'd get a chance to do more than one example. But we're going to do a great example we get into lab today. And so in an hour, I'll see a third of you in lab, and I'll see the rest of you throughout the day. But let's do our first lab. And you read chapter 2 and come back then on Wednesday, and we'll do just more example after example after example. And then I think you'll be in a good position to do the homework. Yeah.
So is the homework